You're watching the 2010 Senior Design Project video for Team Under Pressure, consisting of members Justin Popek, Ann Nielsen, and Lyle Shear. This video will familiarize you with our project by introducing the design concept, explaining the analysis of our design, stepping through the project implementation, covering our testing practices, reporting the difficulties we encountered, and highlighting future enhancements.
A difficulty plaguing many developing countries is the lack of infrastructure for handling common problems. Our team recognized that a shortage of resources in these countries could create dangerous situations for public servants, and personal fire protection gear costs several $1,000s to purchase and maintain. Our mission is to create an effective, low-cost, and safe fire protection robot and control system for areas of the world with limited resources. This is also ideal for wide-scale disaster areas, such as the recent tragedy in Haiti, that cripple the emergency response system. For our business strategy, our team proposes to sell both the hardware and software components. Our company would be structured similarly to the One Laptop Per Child initiative in target underdeveloped nations. To increase exposure and resources, we will partner with existing organizations such as the International Firefighters Association and the United Technologies Corporation. With partnerships like these, we can distribute and deploy at a global scale more effectively.
Our initial project concept was to create a simple autonomous firefighting robot that could be alternatively controlled by a remote device. After further research and requirements gathering, we realized that a fully remote control robot was more appropriate for firefighting. We reviewed the mechanical requirements and the Imagine Cup design requirements, and then developed an overall integrated architecture, including two main components. The first component is the remote-controlled vehicle, which includes open-source hardware, such as the Arduino microcontroller and the Linksys router. The second is the ground control station, which uses Microsoft technologies such as the .NET framework, a Silverlight web application, and an Xbox 360 remote control. Using this architectural plan, we drilled down into the exact components necessary for our system. The Arduino microcontroller is the source of our robot's logic processing and main source of decision making. The GPS shield is an Arduino shield which extends the basic abilities of the Arduino to provide location-based data. The motor controller is another Arduino shield which allows the low-voltage Arduino to power a higher voltage motor. The motor controller will be used to power the fire extinguisher motor. The Arduino shield extender allows us to attach the multiple shields we're using. A Linksys WRT54G router provides wireless communication for the robot. The router is modified to run the OpenWRT Linux operating system, and a serial port is added for Arduino communication. We're using an ABC fire extinguisher. The self-contained unit provides an easy means for refilling the extinguishant, and the standard size allows us to quickly and easily swap the canister for various fire types. For a live video feed, we're using a Panasonic network web camera. The camera connects directly to the robot's router to lighten the processing load of the Arduino. Another Linksys router is used for wireless communication at the base station. A Silverlight application will be running at the base station. An Xbox controller will interface with the Silverlight application to control the robot's movements using natural button mappings. Choosing the right chassis for the robot was a vital step in creating a usable unit. After looking into standard robotics chassis, we determined that they were too small to properly hold the fire extinguisher and handle the thrust created by engaging the canister. Our search for a suitable chassis eventually led to Power Wheels, as in the popular ride-on children's toys. We acquired two used units, each containing two motorized wheels. After testing the motors to ensure they were in a usable condition, the vehicles were stripped down. The existing plastic wheels were not suitable for firefighting conditions, so we purchased generic metal and rubber wheels to replace them. The wheels were modified by removing the original ball bearing hubs and fitting them to attach to the motor assemblies. We used a plywood sheet as the base of the chassis and attached the motor assemblies using wood blocks and screws. The wheels were then attached to the motor assemblies, and our resulting chassis emerged. The finished chassis provides a rigid foundation for the mobile unit and allows for proper mobility and control. The robot is powered by the two 10-volt batteries included with the Power Wheels. Here you can see the motor and motor assemblies attached in their final state. Each motor is 12 volts and requires about 2.5 amps of continuous current and about 4 amps of peak current. This high current requirement was difficult for our current motor controller, so we had to perform additional research to find another professional-grade motor controller. With the improved current provided to the motors, our robot will be able to travel at around 6 miles per hour with an estimated battery life of about 2 hours.
Currently, we have integrated the Xbox 360 controller with our prototype robot by mapping the joysticks to their respective gear assemblies. As the joysticks are moved, the robot responds by varying the analog speed of each motor. Here you can see the alpha version of our software. When the user moves the joysticks, the arrows indicate the current robot state and the video is refreshed in real time.
We implemented several methods to test the mechanical design of the robot and the correctness and performance of the software. We tested the mechanical workings of the robot by manually controlling it and observing the resulting behavior. Our initial interest was getting the robot to drive in the correct direction. For testing purposes, we created a Java program that converted keyboard inputs to commands that were sent to the robot. This allowed for mechanical testing without having to use the Xbox controller. We were able to verify that the motors were turning in the right directions with changing user input combinations, and that the speed was being adjusted properly. At this point, we were able to confirm vertical integration from the Ethernet shield to the motors. After the basic directional tests, we were able to perform various other tests on the robot. We were able to check the chassis alignment and directional consistency using long hallways. Narrow spaces, such as doorways, allowed us to test the maneuverability and response of the steering. Because the robot is meant for non-ideal environments, we took it outdoors to introduce it to different terrains. There, we were able to observe the tire traction and turning abilities, as well as the component's resistance to the jostling created by driving on more rugged surfaces. Being outdoors also gave us the opportunity to test the range of our robot. To test the Arduino code in a more isolated environment, we unit tested the Arduino shields by creating small C and C++ test projects. To test the Silverlight interface, we created a web service that mocked the communication to the Arduino. This decreased debugging time and allowed for concurrent development of the Arduino and the ground control station code. Initially, our plan was to modify the router to communicate with the Arduino using a serial converter. But we encountered issues compiling programs on the OpenWRT operating system that we had installed on the router, and we were unable to establish serial communication with the Arduino. Instead of continuing with the serial converter, we opted to use an Ethernet shield for the Arduino. This solution created a simple interface between the router and the Arduino, and allowed us to establish wireless communication to the robot.
There are a few enhancements that will be made to our project in the next 3 weeks. We will create a metal cover for our electrical components to protect the robot from any damage near a fire. We will also be integrating the Live Maps API with our GPS data. This can be shown to the user by overlaying a detailed map that Microsoft provides.
Thanks for watching our project intro video, and we hope that you can attend eWeek this April.
Whee!
Can't wait to see you there.